In this video, we are going to discuss related rates. Related rates come from problems when you'll have multiple variables, such as the Pythagorean theorem. We have three variables, leg, and hypotenuse. Well, if you have a right triangle that's changing in size, all three of them are changing at the same time. There are rates for the bottom leg, rates for the other leg, that doesn't look much like a right triangle, and a rate for the size change in the hypotenuse. The idea behind a related rate problem is if we are changing the size of a right triangle, there is a speed, in which case the vertical leg is changing. There is a speed in which the length of the bottom leg is changing. And there is a speed in which the hypotenuse is changing. But because there is the Pythagorean theorem that governs the total equation for the side lengths, there will be an equation that governs the speeds for the rates as well. That's what related rates are all about. We are going to try to use implicit differentiation so we can answer questions about rates when the problem contains multiple rates, such as speed of hypotenuse changing, speed of leg changing, speed of other leg changing. The general guide to solving these types of problems, the very first thing you have to do is make sure you understand what's going on. A lot of times, if you can draw a picture, that helps create and helps people see things. But you have to understand the problem first, and then you've got to connect the stuff that you're given or the stuff that you're told to the stuff that you don't know. A lot of times that involves recognizing something familiar, searching for a pattern, adding in some other fact that you always know is true, breaking it up into chunks so that you have cases, work backward, basically build in steps, use whatever you can, but somehow you're going to have to connect what you're told to what you don't know. When you're able to do that, that's generally you will build an equation that you can work with. After you build the equation, you've got to do the math to carry out the plan, do the stuff that you've got to know how to do, and then at the end, look back to see if it kind of makes sense. Specific to related rates, we'll fill in some of these details and kind of give you a guideline toward the end of the lesson. Here's our first problem. Air is being pumped into a spherical balloon so that its volume is increasing at a rate of 80 cubic inches per second. How fast is the radius of the balloon increasing when the diameter is 40 inches? Well, first of all, do you understand what's going on in the problem? The idea is we have a spherical balloon, and I know it's a circle, not a sphere, but here's our balloon. As you're blowing air into it, it's going to blow up and get bigger. There is a speed, in which case there's a speed in how fast there is a speed measuring how fast the volume of the balloon is increasing. At the same time, there is a speed measuring how fast the radius of the balloon is increasing. Our goal is to figure out how fast is the radius increasing, which we could get from right here. I mean, that's the question. Well, what's one thing that you know already? If this is a spherical balloon, okay, we know the diameter is 40. And because the diameter is 40, what will that tell us about the radius? Okay, so we know we're concerned about what's going on when the radius is 20 inches. Here's some other big clues. Spherical volume. Isn't there a formula for the volume of a sphere? Well, that's what we would start off with. we would introduce some other stuff that we know. And frankly, if you don't remember the formula, go look it up. This is the volume, the formula for the volume of a sphere. Now here's the issue that we have. Normally when we're working with problems, you start substituting pieces in. And you look at it and say, oh, hooray, I know what the volume is, so then I can figure out the radius. Do we know the volume? We know the rate. Well, we don't. We could figure out, if we went through and plugged in the radius of 20, that would tell us the actual volume when the radius is 20. Were we asked for the volume, though? No. At no point did they say, what is the volume? So we don't care what the volume is. The piece that we need is the rate of increase, the rate of change in the radius. We don't have that anywhere. But we can introduce them, we can create rates by taking the derivative. On both sides, we will take the derivative with respect to the variable r and then see what we get. Taking the derivative of volume with respect to r gives us dv dr, the rate of change in volume as the radius is changing size. Take the derivative on the right-hand side. That's 4 pi r squared. But, I'm sorry, I said something backward that I have to back myself up a little bit. We were not looking at the rate of change in volume as the radius is increasing. Because this is per second, I should have been taking the derivative of the volume as time is changing. And that's where I messed up. I wrote the wrong variable. I apologize for that. But to fix it, we can come back and say, here we've got all those pieces. We still take the derivative. It's still 4 pi r squared. But the problem that we have now is, since we're not taking the derivative with respect to the variable r, it's respect to the time, r is a function of time. So the chain rule applies with implicit differentiation. After we take the derivative, we still have to multiply by the derivative of the inside piece. But the derivative of r is just going to be dr dt. This is where related rates are coming in. The overall equation relates volume to radius. By taking the derivative, we can then create an equation that relates the volume rate with the radius rate. And this is now stuff that we know a bunch of information about. We know the rate of change in the volume. We were told that was 80. Now we could plug in 80. We know the radius was 20. So we can plug in 20. And all that's left in terms of variables is the rate of change in the radius that we cared about. When we solve this equation in the red, we're done. So we would be able to then say 20 squared is 400, times 4 is 1600. So we can wind up with 1600 pi, 1600 pi, times the rate of change of the radius with respect to time. We'll just divide by the 1600 pi. 1600 pi. That cancels out. On the right-hand side, we have the rate of change in the radius as time changes. And we've just got to simplify our fraction now. Cancel out the zeros is easy. 8 over 160. We can divide both by 8. So we get 1 over 20 pi is the rate of change in the radius. And that is inches per second for our label. And we are completely done. General outline behind the problem was there is a governing equation. A lot of times it may be an equation that you will build. Maybe it's an equation that you will look up. But once you've got the equation, you can take the derivative so that it introduces rates, specifically the related rates. You'll need to be careful about doing implicit differentiation correctly so that way we wind up with something that is beneficial. After taking the derivative with implicit differentiation, you can then substitute in the values that you know, which generally allows you to solve for the thing you are looking for. We can see this process again here. A ladder, 12 feet long, rests against a vertical wall. If the bottom of the ladder starts to slide away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 7 feet from the base of the wall? So could you draw a picture for it? You have a mental image of what's going on. We've got this ladder, and it's a vertical, or we have a vertical wall, which tells us we've got a 90-degree angle. That's what vertical means. And right now we have a 12-foot long ladder resting up against the wall. When this starts sliding downward or outward, we know the ladder is going to have to start sliding down. Eventually, it's going to be sitting down until it winds up laying flat. But there will be a point somewhere when you're 7 feet from the base of the wall, you will still have a 12-foot ladder. We know with Pythagorean theorem we could figure out the height, but we don't want to know the height. We want to know how fast is it falling. Overall, though, here's our basic picture. There we go. Here's our picture. Well, what is the governing equation? In general, we'd have legs squared plus legs squared. Come on, where's my other square? Equals the hypotenuse squared. And we know the hypotenuse is a fixed 12. That doesn't change. Well, we can now take the derivative of this piece. If we take the derivative of both sides with respect to time, because time is what's changing here, we could then get 2 times a, but this leg length a is a function of its height, or of time. It's changing. So we would have to use the chain rule with implicit differentiation to get dA dt. Similarly, we'd have 2b, but the height of this piece is still a function. So we'd have dB dt, and the derivative of 144 is just the constant 0. And so we've built ourselves an equation now. We built an equation, and we can now start plugging in pieces that we know. Well, what other information is there? We have 4 pieces of unknowns right now. We need to know the value of A, which is the length along the bottom. We need to know how fast the bottom is changing. We need to know the height, and we would need to know how fast the height is changing. Well, are there pieces we already know? Which ones? Okay, we know the rate in which it's sliding away from the wall. That's dA dt. That's a 1. So 2 times A times 1. Do we know the value of A? Yeah, we were told that's a 7. Plus 2 times B. Do we know the value of B? We don't know it now, but we can get it. That's where we could come back and use the Pythagorean theorem. We already have legs squared plus legs squared equals hypotenuse squared. So we could figure it out. 49 plus b squared equals 144. So subtracting 49 would give us 95. Therefore, b is equal to the square root of 95, which is not even going to simplify because that's 19 times 5, a pair of primes. So it's just the square root of 95. So we can plug that in. Square root of 95 times what we are trying to figure out. The rate of change in the height along the wall, and we've now built ourselves an equation. We just got to solve it now. 2 times 7 times 1 plus 2 times the square root of 95 dB dt, the rate of change in the height along the wall as time is changing. Subtract 14. So we'd have 2 times the square root of 95 dB dt equals negative 14. And dividing by the constant, we'd have dB dt equals negative 14 over 2 times the square root of 95. That simplifies to be negative 7 over the square root of 95. And our label for that is feet per second. Does that make sense? Well, it is a negative rate. That kind of makes sense. That should happen because the negative rate tells us it's getting shorter. And because this is falling downward, shouldn't that distance be getting shorter? So in that regard, it kind of makes sense. But we've got our overall answer right there. And we could plug this into a calculator and get an approximate value. This is the exact number, but if we'd like to get an idea of about what we would need, we could then say 7 divided by the negative root of 95 and get the approximate value of negative 0.718 feet per second, which is also good because we're not getting something like, oh, it's falling at a rate of 20 feet per second. 20 feet per second wouldn't make sense. Here's a third example. A water tank is in the shape of an inverted circular cone. Okay, so what does that look like? Well, inverted circular cone, there's our water tank. The base radius is 3 meters, and the height is 5 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is increasing when the water is 3 meters deep. So basically, when you start pumping water into the tank, we're going to get to the spot when this water is 3 meters deep and this height is going up. How fast is the water level going up? Obviously, because there's very little water here, right away, this is a rate that's very, very high. But as you get wider toward the top of it, it's going to start slowing down with how quickly the water level is rising. Now, to begin this problem, we have to start and say, do we have an equation that starts us off? How about it's a cone, and so we're looking at the volume of a cone. This is one that maybe you need to look it up, but it would be 1/3 pi times r squared times height. And each one of those pieces, volume, radius, and height, those are all functions of time. So when we come through and take the derivative with respect to time, we're going to have to pay attention to the idea that we have a product of functions. We have pi r squared as one function, 1/3 pi r squared, because pi is a constant, 1/3 is a constant. But then we're multiplying by h, and h is another function. When we take this derivative, we will have to use the product rule. Still using implicit differentiation, but it'll be product rule as well. So, what is the derivative of v? That would be dv over dt. On the right-hand side, take the derivative of 1/3 pi r squared. Well, remember the formula for product rule? First times derivative of the second plus second times derivative of the first. So taking the derivative here, we would have the first function. And I accidentally left off the pi. I'm just going to write that as pi over 3 instead of 1/3 pi. First times the derivative of the second. So what's the derivative of h? It would be 1, but because it's a function, we've got to apply the chain rule. That will be dh dt. So I actually want to write this step out further, because I think seeing it, that would be the derivative of h. That would be our g prime. Then we'll say plus the second times the derivative of the first. And I'm just putting in this extra step so that we could see this perhaps a little bit more clearly. Pi over 3 r squared. The derivative of h would be 1, but because it's a function, that's dh dt. The derivative of pi over 3 r squared, we'd have pi over 3 times 2r, but because r is a function, we're still using chain rule with implicit differentiation. That's dr dt. And now we have created a piece that gives us our related rates. Let's start plugging in the pieces that we know. So, the base radius, okay, so if the water is being pumped into the tank at a rate of 2 cubic meters per minute, that's the volume. That's the rate of change in the volume. So we could say this piece is a 2. So pi over 3. We're then looking, find the rate at which the water level is increasing when the water is 3 meters deep. Well, because the water is 3 meters deep, that tells us the height of the water will be 3. Okay, so our height is then 3. Do we know the radius when the height is 3? Right, well, we're told the base radius is 3. That radius is 3. We need this radius. This is where similarity from geometry will come into play. We know the base radius is 3. The overall height is 5. We could set up a proportion using similarity where now the height of the water is 3. We need to know the radius. Cross multiplication would yield 5x equals 9. Dividing by 5 tells us x is equal to 1.8. So our radius at this point is 1.8. So we're still using the stuff that you learned in geometry. We're still using the stuff that you learned in algebra. And so we'd have 1.8 for the radius times pi over 3 times 2 times 1.8. You'll notice we're just plugging in all the stuff that we have. And we now have dh dt, dr dt. Which piece are we looking for? We want to know the rate in which the water level is increasing. That is a piece that will be dh. Do we currently know dr dt? The 2 here came from the volume. At this particular point, we're going to leave it alone because we don't know what the rate of change in the radius is. So we have to come back to here and now say, start plugging in all this other information. We'll simplify it a little bit. 1.8 squared is 3.24. So we would have 2 equals 3.24 over 3 times pi dh dt. 3 over 3 cancels. So we'd have plus 3.6 pi dr dt. And I'm going to note 3.24 divided by 3 is just 1.08. And so here we go. We're trying to get dh dt completely by itself. So we could subtract off the 3.6 pi dr dt. I want to pause for a second and ask you, the students in the class, a question. Do you want to go through and solve it right now so that we have dh dt equals blob? Perfectly valid strategy. Or would you rather go through and note, so abruptly class decided they just want to solve it, get the dh dt equals the big blob, understanding the fact that because dr dt is still a variable, it's going to be in our equation. So from here, we could subtract the 3.6 pi dr dt, which would then yield I got to extend the page. 2 minus 3.6 pi times the rate of change equals 1.08 pi dH dt. So we would just need to divide by 1.08 pi. Splitting this piece up, whoa, too far. That would be 2 over 1.08 pi minus 3.6 pi over 1.08 pi dr dt equals dH dt. Well, of course, pi and pi would cancel. And these are pieces that we could then divide out to get approximate values or decimal values or fractions. We could wind up simplifying a bunch of pieces. So after simplifying our two fractions, we obtained 50 over 27 pi minus 10 over 3 dr dt equals dH dt, which is what we wanted. In terms of a strategy, you'll note this is kind of where we've been following specific to related rates. Reading the problem carefully helps you to understand what's going on. In every instance so far, we've taken the time to draw a picture. Introducing notation was creating the equations, whether it was looking up something for volume or Pythagorean theorem or something. You found some governing relationship, and then by taking the derivative, we were able to express the given information in terms of derivatives, start plugging in absolutely everything that you needed to do, and then finish off the rest. This was taken directly from your textbook. All right, so here's our last one that we'll look at. A car is traveling east at 60 miles per hour. Another is traveling north at 50 miles per hour. And both are headed for the intersection of two roads. At what rate are the cars approaching each other given these distances? First off, can you draw a picture? One car is traveling east, and it's traveling at a rate of 60. One car is traveling north at a rate of 50, but, wow, that was slanted. But they are traveling for the same intersection where, presumably, they're going to meet. You'll note when they talk about the distance between the two, we're not talking about distance along the roads. The distance between the two cars is here. Now, of course, as they're driving, this distance could be slanted all over the place. But as it's traveling, as cars are traveling, this distance is definitely getting shorter. We are asked, what is the rate the cars are approaching each other? So we're looking not for the distance, but for the rate of change in the distance. What's our governing equation? Pythagorean theorem, how we'd have legs squared plus legs squared equals the hypotenuse squared. Is this hypotenuse fixed? No, it's not like the ladder problem. This is the hypotenuse that is changing. And so when we take the derivative of both sides with respect to time, we would have 2a dA dt, and I'm going to use this one for our a, plus 2b dB dt There's our B, and that's going to equal 2C dC dt. What pieces do we currently know? We know distances. The first car is 0.4 miles. So it tells us 2 times 0.4. Scotty, you also told us the rate. dA dt, the speed of the car, the rate of the car, is 60. Okay, what else? Okay, so we had 2 times 0.3, and its rate is 50. That would give us 2C. We're not told C, but could we figure it out? Yeah, Pythagorean theorem, 0.3 squared plus 0.4 squared equals the C squared. If we solved that, we'd get C is equal to 0.5. So 0.5 dC dt, which is what we're trying to figure out. So 2 times 0.4 is 0.8. 0.8 times 60 would be 48. 2 times 0.3 is 0.6. 0.6 times 50 is 30. 2 times 0.5, that's 1. So we'd wind up with dC dt. And so we'd have 78 is the rate of change. And that is going to be measured in miles per hour. So at this particular moment in time, with these cars traveling at this particular speed along these particular paths, we know they're actually approaching each other at 78 miles per hour. All told, related rates have just this one learning objective. We will have to use implicit differentiation. You create a governing equation, whether it's based on something in geometry, whether it's based on a formula you're given, whether it's based on anything. You'll have a governing equation. Taking the derivative, using implicit differentiation, will introduce the related rates, substitute in all the pieces that you know, solve for what you don't.